All right, let's talk about making inferences and predictions with the multiple regression model. So here's our multiple regression model. The y value is essentially a weighted sum of the predictor variables, and individual values differ from the average by a random amount, specifically a random normal amount with the same typical deviation everywhere we look. So unfortunately, since we only have a sample, what we measure aren't the betas. These would be the coefficients if we had data on every single member of the population. With our sample, we're only approximating what these coefficients are. We basically get our best guesses out. So we know that what we measured from the sample is wrong, but the good news is that we're never going to be that wrong. Remember, we have this concept called the standard error of a quantity. The standard error of a quantity tells us the typical difference between what we measure and the truth. So what we want to do is we want to figure out, okay, well, how far away are the measured coefficients likely to be from the betas? What are the standard errors of the measured coefficients? Now, what's interesting in the multiple regression context is that the size of the standard error actually depends on the amount of correlation between the predictors. And when things are correlated, they share the same amount of information. So in other words, the size of the standard errors depends on the amount of redundant information among them. So let's kind of see how this works. Okay, so like I said, this is the truth, beta I, that's what we'd like to know. It would be the coefficient if we had all the data on all individuals. We estimate beta by B, the coefficient measured from our sample here. So B is most definitely wrong. It's not going to be equal to beta, but it's not going to be that far off from the truth. We expect BI to be off from the truth by about a standard error or two, just due to natural sampling variability. So there'll be a formula that lets us know what the standard error is. What do we do with it? Well, we make a confidence interval for the beta, for basically truth here. What we know is that, okay, the standard error of a coefficient gives us the typical difference between the truth and the value that we actually measured from the sample. And what we do with this is that we know that we can be about 95% confident that the truth is within about plus or minus 2 standard errors away of what we measured. So remarkably, and this is when the regression model is appropriate, statistical theory tells us that the measured coefficient in the sample is never that far away from the truth. You can actually come up with an equation that tells you the standard error, the typical difference between the truth and what you measure. And it turns out that 95% of samples have their measured coefficients be at most 2 standard errors away from the truth. So we can be 95% confident that the truth is within about 2 standard errors of what we measure. Okay, now the standard errors themselves, there's a complicated formula for it. We're not going to worry about it, but we can get it from the regression output fairly easily once we do summary. So here's our salary model predicting education experience in months. My estimated coefficient of education is 93. Now, obviously, that's not going to be equal to the true coefficient if I had all the data, all employees. The standard error in the column labeled STD error here is about 18, implying that, okay, what I measured, 93, is probably off from the truth by, about a standard error or two, maybe my 18 by 36. So I get a bit of an idea for how far off what I measured is likely to be from the truth. Okay, so let's talk about what affects the standard error. How much uncertainty am I going to have with my estimates? Well, in a simple linear regression equation, we introduced an equation for the standard error. I'm going to rewrite it this way. The standard error of the slope is equal to the standard deviation of the y values in the data divided by the standard deviation of the x values. And it's also given as r squared and n. All right, oops, I had a phone call, so I'm back to where we started. And let me get back to, oh no. Let me get back to the slides. Here we go. Let me make sure it's actually still recording. It is, good. All right, so in a simple linear regression, the typical amount of error that we have with the measured slope is proportional to the standard deviation of the x variables. We saw the more spread out the x variables were, the smaller that standard error was, and it's also related actually to the r squared of the regression and also to the sample size. So the standard error increases with the amount of scatter around the regression line, basically as the more and more scattered the y values are. The standard error gets smaller as the sample size gets bigger, and the standard error gets smaller as the x's are more and more spread out. Okay, the equation for the standard error in the multiple regression context looks like this. It's actually the exact same formula except with this additional term right here. It involves 1 minus r sub I squared. What is this ri squared? Well, ri squared is the value of r squared that you would obtain if you fit a model predicting the variable xi from the other x's in the data set. And so here's what's interesting about the formula for the standard error of the coefficient in the multiple regression. Basically, as xi is more and more redundant with the other predictors, in other words, we can predict xi better and better from the other variables, ri squared increases. And as ri squared increases, what happens is that this number gets closer to 1. 1 minus that number gets closer to 0, and the standard error gets bigger. So, what is the upshot? Well, if r sub I squared is large, what that means is that xi can be predicted well from the other variables. In other words, the information it contains is pretty redundant with the other predictors in there. And what's going to happen is that large values of ri squared are going to yield large standard errors. So the overall lesson is that if one particular predictor has a lot of redundant information with the other predictors, it's going to be very difficult to estimate the coefficient. That coefficient is going to have a large standard error. Okay, so this sort of makes sense. So, all right, if we're trying to isolate the association between y and a particular predictor, that's going to be hard when there's a lot of correlation. So the correlation between our predictor of interest and the other predictors makes it very difficult to disentangle what information about y is really due to xi and what is due to the other predictors. Since when there's a lot of correlation, all of the x's are changing essentially simultaneously, it's difficult to really pinpoint, okay, when xi changes by 1 unit, but all the other predictors are held constant, they're identical, what's the expected average change in y there? It's hard to figure out because everything's moving all at once. It's difficult to have just xi vary by itself while keeping all the other variables constant. So, since the coefficient is the difference in average value of y among individuals who differ in xi by 1 unit who are otherwise identical, its value is very difficult to estimate when there's correlation because all the predictors are changing simultaneously, so it's really difficult to imagine or to find individuals who are identical in all regards except for xi. So, the more information that xi has that's redundant, the more difficult it is to estimate the coefficient. So we've seen this before, actually. Imagine predicting body fat percentage from abdomen and thigh circumference. Well, it's going to be really difficult to isolate how the average body fat changes with abdomen alone because the other predictor in our model changes almost identically with abdomen. As abdomen goes up, so does thigh circumference. As abdomen goes down, so does thigh circumference. So isolating the effect of body fat percentage in abdomen is going to be difficult. So the problem is that basically the information that abdomen has about body fat is essentially the same as the info that thigh has about body fat. And so the model has a really hard time kind of divvying up what information is due to abdomen, what information is due to thigh circumference. It has a hard time nailing down the value of the coefficient, and the standard error is large. Okay, so how do we quantify kind of how much correlation, how much redundant information is in our data? Well, we can look at the variance inflation factor of a coefficient. So the variance inflation factor, or a VIF, tells you how much that the correlation in redundant information has degraded the precision of the estimate. So the VIF of a predictor is equal to 1 over 1 minus Ri squared. Remember, Ri squared is the value of R squared for a multiple regression trying to predict that value of X from the other predictors in the data set. And what the VIF tells us, well, if we take the square root of the VIF, that tells us the factor by which the standard error has increased due to correlation with the other predictors. So a VIF of 1 is perfect. That means that the information in X is not redundant at all with the information contained in the other X's. If I get a VIF of 5, that indicates a large amount of redundancy. If I have a VIF of 5, that means that Ri squared is 80%. So a multiple regression model predicting xi from the other x variables would have an R squared of 80%, and that's huge. So in essence, 80% of the information in X is already contained in the other predictors. And so what that means is the standard error of my coefficient for that X is the square root of 5, or about 2.2 times larger than it would have been had all the X's been independent. All right, so how large of a VIF is considered large? Well, there's really no agreement about that. Some people say that VIFs of 5 are always large. Others say 10. I have a slightly different guideline. What I do is I look at R squared of the multiple regression model, not R squared adjusted, and I calculate 1 over 1 minus R squared. And then my criteria is that if a variable has a VIF bigger than this threshold here, 1 over 1 minus R squared, then the amount of information is fairly redundant. Why is that? Well, if the VIF is bigger than this quantity, what that means is that the variables do a better job at predicting X than they do at predicting Y. And that's not really what you want out of your model. You want your predictors to be predicting Y, not themselves. And so that's when I'm going to consider it to be kind of an issue. So each variable is going to have its own VIF. And if we have a decent number of predictors having large VIFs, we say the model suffers from multicollinearity. Basically, there's so much redundant information in the predictor variables that it's very hard to isolate the association between Y and any one particular predictor. All right, so how do we get them out of R? Well, we actually need to load in a new library, either library car or reg class. And doing VIF of a model spits out the variance inflation factors. With our salary data, we see the VIFs are essentially 1, indicating that there's very little redundant information actually going on between these three predictors. If I look at the BODYFAT example, well, the VIFs are actually really quite large. We see that weight has a VIF of 33.5, so I can very accurately predict weight from the other predictors in the data set. Same thing goes, say, for hip circumference. So these are very large VIFs. I'd be worried here. The quality of those estimates are degraded. They're going to have very large standard errors. So what do we do when we have multicollinearity? Well, actually, it's not all that bad. It doesn't invalidate the regression model. All the presence of multicollinearity is telling us is that it indicates that the correlation among the x's is big enough for the coefficients to be poorly estimated. In other words, the standard errors are just a lot bigger than what they could have been if all our predictors were independent. So in the descriptive modeling context, the goal is to estimate all the coefficients as precisely as possible. So multicollinearity is a bad thing. Basically, our standard errors are pretty big, and we'd like for them to be smaller. Nothing we can really do about it, but that's just the way it is. In predictive modeling, actually, multicollinearity is pretty irrelevant. We don't really care about the quality of the coefficients and their estimates. We only care about how well it makes predictions on new data, and multicollinearity doesn't really affect that. All right, there's some additional insights into standard errors that the formula provides that are maybe a little bit surprising. So if we look at the standard error of a coefficient in a simple linear regression, and then look at the standard error of that predictor in a multiple regression, very often that error is going to be smaller, less than the standard error in the simple linear regression. And so this is actually a good motivation for doing a multiple regression. We know that the variation in Y in the data that we see can be attributable to many different sources. And if we really want to know, okay, what variation in Y is due to a particular predictor, it's good to account for those other sources of variation. And so what's happening is that the standard error, how far off we think that coefficient might be from the truth, actually gets smaller the more and more we account for extraneous sources of variation. As long as each of the predictors in the model is basically a good predictor of Y. It's not a junk predictor, and there's not too much correlation in the variables. So basically what ends up happening is that the extraneous variation in y that's not due to xi is taken away when we fit that multiple regression model, leaving our estimate of how y varies with xi much more precise. Now, that's not always the case. It can be the case that the standard error of the coefficient is larger than the standard error in a simple linear regression, and that's going to occur when there are bad predictors in the model, or if there's just a lot of redundant information amongst the predictors. And so this actually provides an argument against doing a bad multiple regression model. If there are unnecessary variables, this provides an argument for throwing away those unnecessary variables if possible. When you throw away junk predictors, the precision of your coefficients actually gets better. Okay, so in the salary data set, we saw there's very little correlation among the predictors, and in fact, the standard errors get smaller in a multiple regression model. So the standard error of education is 19.8 in a simple linear regression. If we add in experience into the model, well, we've accounted for some of the variation in salary due to experience, leaving us with a bit more precise of an estimate of the coefficient of education from 19.8 to 19.47. Not a huge change, but a small decrease nonetheless. Likewise for the effect of experience, standard error of 6.5 in the simple linear regression to 5.87 in the multiple regression. Now, in the TIPS data set, we actually get the opposite happening. So the standard error of Bill in a simple linear regression model is 0.0415. If I throw in party size, well, I find the standard error is actually a bit larger. I'm more uncertain about the coefficient of Bill in a multiple regression model than in a simple linear regression model. Well, what happened? Well, in this model is actually an extraneous junk predictor that I don't need. If I look, I see the p-value of party size is 0.2. It's not statistically significant, so adding party size into the model that already contains Bill doesn't help me out. Having a junk predictor in the model makes the standard errors of the predictors that matter actually worse. So I'd want to get rid of party size in this model and just predict tip percentage from Bill size here. Body fat example, we see a large degradation of standard errors as well. Predicting body fat percentage by abdomen itself, we get a standard error of 0.026. In a multiple regression model with abdomen, chest, and weight, I find that that standard error has increased by almost a factor of 2.5, from 0.026 to 0.065. So in this case, two issues. One, this model has an unnecessary predictor. Chest is not significant, so I could actually exclude it from the model. And I know there's a lot of redundant information going on between the predictors here. All those serve to degrade the accuracy of my coefficients. All right, so if I look at the VIFs of the coefficients in that model, I can kind of see that that's the case. The cutoff for a large VIF would be 1 over 1 minus r squared being about 72% here, or a VIF of 3.6. And I see that all three predictors have a VIF that exceeds that, so multicollinearity is a problem. It doesn't invalidate the model, it just is saying that, hey, there's a lot of redundant information going on here. And if I were to take the square root of 7.27, I accidentally didn't do that here. The standard error of abdomen is the square root of 7.27, or about 2.6 times larger than it would have been had all three predictors been independent. So I see there's a huge correlation between some of these predictor variables, a lot of redundant information flying around. I'm going to skip the NFL example. You can review that on your own. We do not see multicollinearity being a problem in this case. Okay, so armed with the standard error, we have an idea for how far off what we measured the coefficient to be is likely to be from the truth. We can convert that into a confidence interval. So when the regression model is appropriate, there's a 95% chance that the measured coefficient will be at most 2 standard errors away from the truth. So by extension, we can be 95% confident that the truth is within plus or minus about 2 standard errors away from what we measured. There'll be formulas that tell us the standard error. We'll get that from the regression output, and we can actually just ask R for confidence intervals about the regression coefficients. You can specify the level as well, and in this case, predicting the number of wins from these three predictors for the NFL dataset, we can be 95% confident that the coefficient beta turnovers is somewhere between these two numbers here. And so just remember, confidence is talking about the probability that our procedure actually gets it right. So with a new random sample, the data points are different. The confidence intervals we would construct are different as well. Some confidence intervals we make get it right. Some confidence intervals get it wrong. The meaning of confidence refers to the long run fraction of time that our confidence intervals actually do get it right. So here the truth is that beta is equal to 5 in this case. Here are the confidence intervals for 100 different random samples. And we see that most of them get it right because the interval contains 5. But the ones that don't, in red, get it wrong. In the long run, 95% of the intervals get it right for a 95% confidence interval. All right, we can also use confidence intervals to gauge significance. The confidence intervals gives a range of plausible values for beta. So if 0 is inside the 95% confidence interval, 0 is a plausible value for the coefficient. And if the coefficient is 0, the dependence of y on x disappears. Because if beta I is 0, then 0 times x is just 0 here. Okay. So making predictions with our regression model, easy as just plugging in the values of the x's into the regression equation. And we might be predicting one of two things, either the overall average value of y at that combination of x's, we'll call that y hat, or a particular individual's value of y who happens to have that combination of x's. Our best guess, the point estimate, is going to be the same regardless, just plugging in those values into the equation, but the amount of uncertainty is going to be different. So let's say we want to predict the average value of y among all individuals with some particular combination for the x's. Well, assuming the regression model is appropriate, there's actually an equation that tells us the standard error of the predicted average value. So we'll actually know how far off our predicted average is likely to be from the truth. And it turns out that taking our point estimate and going about plus or minus 2 standard errors will give us a 95% confidence interval for the true average value of y at that combination of x's. Now, if I want to make a prediction regarding an individual, well, there's once again going to be a formula for the standard error of the predicted value, and the standard error is always going to be larger than the standard error for an average. And that's because who knows how far away the individual is going to be from that average. They're away from the average by a random amount. But once again, there's going to be a 95% chance that the individual's value will be within yp plus or minus 2 of its standard errors. So later on in the end class activity, I'll talk about how to get 95% prediction, 95% confidence intervals. The key for you is to remember which one you actually want. If you're predicting the average value of y, you want the confidence interval. If you're predicting an individual's value of y, you'll want the prediction interval. All right, so that is going to be it for the lecture. I have a few slides that summarize some of the quirks regarding the coefficients, about how the coefficients can go from positive to negative, x can go from significant to not significant depending on models, which you can review. And also on our activity day, we'll actually walk through how we do all this stuff with R, making visualizations, fitting the model, getting the summary, what the numbers mean, how we do the partial F test to see the significance of a set of predictors, getting variance inflation factors, getting confidence intervals, and also making predictions. So we'll see you guys then.